Okay, so let's have some fun with modular arithmetic. So I'm going to answer this maybe innocent looking question. What's the last digit of 7 to the 100th power? Um, and what if I told you you can even have a calculator to answer this question? So actually, if I give you a normal calculator, so I just put 7 to the 100th into Google, which is about as powerful as like a standard calculator. It has however many digits of precision. It looks like it goes to 7 digits. But this number is so big. It's 7 to the 100th power. It has Google has to put this in scientific notation. So this is like, 3.23 whatever times 10 to the 84th. So this is a huge number. It has 84, or I guess 85 digits it would be. Um, and just for reference, the number of atoms in the universe is only about this big. So the number we're trying to deal with here is maybe like 10 or 100 times more than the number of atoms in the universe. Um, and a normal calculator putting this in scientific notation does not tell you the last digit. This is really just telling you the first however many. Okay, sorry about that. I dropped the phone while I was recording. So I was in the middle of saying this only tells you the first like 8 digits of the number. It does not tell you the last digit. It cuts it off because it puts it in scientific notation, and it only gives you the most significant digits. And the digit in the ones place is not considered significant for a number this big. So, um, how are we going to do this? We are going to do this with modular arithmetic. And so the original question was, what's the last digit of 7 to the 100th power? And when I say last digit, of course, I mean in base 10, the way we normally represent numbers. So let me ask a second question that's really the same question. What's the remainder when we divide 7 to the 100th power by 10? And that's the same question because that's exactly what the last digit is. It's the remainder when you divide the number by 10. For example, if I take 1,728 and I divide by 10, it's very easy. This is the easiest thing in the world because of the way we're representing these numbers in base 10 and we're dividing by 10. 10 goes into this 172 times with a remainder of 8. The 172 is just taken from here, of course, and the 8 is just taken from here. It's the easiest division problem in the world. Well, assuming I know all the digits of this, it's the easiest division problem in the world. This one won't be as easy because I don't know all the digits of this, but we'll still be able to do it. So how are we going to do this? This is repeated squaring. So let me start small. And pretty soon I'm going to stop writing mod 10 everywhere. All of this is going to be mod 10, so I'll just write the congruence simple and I won't write mod 10 pretty soon. So I'm going to start finding powers of 7, and I'm not doing anything yet. I just found 7 to the 1, so I haven't really accomplished anything. I'm going to start squaring. 7 squared is 49. That I have to just do in my head or remember it. And then that's congruent to 9. Mod 10. Now I'm going to jump straight to 7 to the 4th because I can get 7 to the 4th based on what I've already done. 7 to the 4th is the same as 7 squared squared. Right? I know that 7 squared is 9, and so I square that. And this I have, Um, this I have to, again, I have to remember this is 81, and so that would be congruent to 1. And then, like I said, I'll stop writing mod 10 everywhere. And then, what? We've got 7. The next one I can do is 7 to the 8th. Right? These powers are actually growing pretty fast. I went from 7 to the 1, 7 to the 2, 7 to the 4, and I'm about to do 7 to the 8th. So I can get a very large power of 7 really quickly this way, which is good because we want to work our way up to 7 to the 100th. So, okay, so I'll keep going. How do I get 7 to the 8th? That's because it would be 7 to the 4th squared. Now this is why this method is called repeated squaring. I'm always taking the last thing I did and I'm squaring it. Because I already know that 7 to the 4th was congruent to 1, I get to just put that there. And then 1 squared is just 1. So then what's going to happen now, 7 to the 16th would be the next thing I can do, because that's 7 to the 8th squared. 7 to the 8th was 1. 1 squared is 1. And actually, you can see that for the last 3, we kept getting 1. Now, if we think about it, that's going to keep happening, because what am I doing each time? To get this one, I took the last one and I squared it. If the last one's a 1, then when I square it, I'm going to get a 1 again. And then for the next one, I'm going to be squaring that one, and I'm going to get 1 again. And I'm going to keep getting 1. 7 to the 32 is... that would be the last one squared, so 1 squared is 1. 7 to the 64th is also going to be congruent to 1. Now I'm going to stop. If I did this again, the next power of 7 would be 7 to the 128th, right? And I'm only going up to 7 to the 100th, so that would be too big. So how do I actually figure out 7 to the 100th? It seems like maybe I'm not really there yet. I have these other powers of 7, so what am I going to do? So 7 to the 100th, I'm just going to make that out of things that I know. I'm going to take a big power of 7, the biggest one I know. Now, what would be left? I guess there's 36 of them left, because I need 100 7s on this side, so I need 100 7s on this side, and I already have 64. So I need 36 more 7s. I can get 32 of them this way. Now I need 4 more, so I get them here. Right? So hopefully it makes sense what I just did. I just found powers of 7 that I know, so that these would add up to 100. And I started by taking the biggest ones I could first. I took 64, and then I said, how many more do I need? I need 36 more. So then I took whatever the biggest number I could that was less than 36. So I did 32, and then I needed 4 more, so I just took them here. Because these numbers do add up to 100, so this is the same thing, and I know... And yeah, so maybe let me emphasize something. If you notice, some of these are equal signs and some of them are congruent signs. Like equals is just 2 lines and congruence is 3 lines. So if 2 numbers are equal, then they are congruent. But the converse is not true. it's possible for two numbers to be congruent mod 10 even if they're not equal. Like 7 and 17 are congruent mod 10 even though 7 and 17 are not equal. I like to write equal signs when things really are equal. For example, this really is equal. What I'm about to write would not necessarily be equal. In fact, I guess it's in fact not equal, but it is congruent. Because 7 to the 64th is congruent to 1. 7 to the 32nd is congruent to 1. And 7 to the 4th is also congruent to 1. So the last digit of this huge number is 1. And by the way, actually let's check, can Maple do this? So Maple can do 3 to the 100th. Can Maple do 7 to the 100th? Yeah, it can. So there's that number. It is indeed extremely huge. And the last digit is a 1. So there we are.